Well, hello again and welcome to our journey into linear algebra, and we've been looking at applications of symmetric matrices, and we looked at conics in 2 dimensions, and we're now going to move into 3 dimensions, and we'll see the story is very similar to what we saw in 2 dimensions, except there are more different options and the calculations become a little bit more difficult. So here's a quadric surface here, as it's called. It's got variables x, y and z. So we've got minus 3x squared plus 4xy minus 4xz plus 2yz is 1. And we'd like to know what this surface represents in 3-dimensional space. So here is the worked solution to this. So here is our conic. And as we did before, we're going to whack this into matrix form. So we're going to write this as little x, y, z as a row vector here, multiplied by this matrix times x, y, z as a column vector. And if you expand all this out, of course, you'll get back to here. Now, how did we construct this? Well, once again, this element here comes from the x multiplied by this number multiplied by that x. So the minus 3 goes there for the coefficient of x squared. Now, there's no coefficient of y squared or z squared, so these are 0. Now the xy term comes from this x times this one plus this y times this one times this x. So we get 2 different contributions to the xy term. The total has to be 4. As we saw before, we love symmetric matrices, so I'm going to share this equally between the 2 places here. Now similarly, the xz term is going to come from here and here, and so I share that equally, and the yz term will come from here and here, and we share that equally to get a nice symmetric matrix A. Now, of course, the computation can be quite difficult if we're going to work through the characteristic polynomial and so on, but there's a slightly cleverer way of doing this to get the eigenvalues. So I claim that lambda equals minus 1 is fairly obvious. That means if I were to subtract 1 from the main diagonal, then you'll see that these 2 rows will be multiples of each other. And if you subtract 1, and so lambda equals 1, I think is a fairly obvious one. So once you've guessed one of the eigenvalues, the next thing one does is to look at the eigenspace. So I'm going to look at the kernel then. The eigenspace for lambda equals 1. We just subtract 1 from the main diagonal, as we saw before for the as we've seen before with eigenvectors and eigenvalues. So you subtract that, and again you can now clearly see that this is a multiple of this one, and indeed this is a multiple of that one. So this matrix, in fact, has rank 1, and that means the nullity is 2, because all of the rows of the matrix are just multiples of this vector 2 minus 1, 1. So that means there are 2 eigenvectors hiding in here, and so I can... Now, we're not guaranteed that they're going to be orthogonal, because they're coming from the same eigenvalue. So I write down a very simple one firstly. If I kill that one, take one of those and one of those, then that will dot product to give me 0 with this. So 0, 1, 1 is a fairly obvious eigenvector. Now I could do something like this. I could write down 1, 2, 0 here, and that would be correct as an eigenvector, but not very helpful from the point of view of getting an orthogonal matrix, an orthogonal diagonalizing matrix. So what I did here was I looked at these 2 here and said, well, if I put a 1 there and a minus 1 there, doesn't matter at the moment what goes here, that will be automatically orthogonal with this one. And then I look back to one of the rows here, it doesn't matter which one really, look at the first row. We've got minus 4 times something, and then we've got 2 plus 2 is 4. So I want to kill that. I need a minus 4, so I'll just take one of those. And so that I call that creative cookery. You cook up the eigenvector, the second eigenvector, to make sure it is orthogonal with the first one. because there's no guarantee of that automatically happening because the eigenvectors are coming from the same eigenvalue. Okay, so now we've got two eigenvectors. We want the third eigenvalue. Now, since this has geometric multiplicity 2, it must occur at least twice in the characteristic polynomial. So I have lambda equals 1 and 1. And then I can use the trace. The trace, some of the eigenvalues is the trace of the matrix. So the trace of the original matrix was -3, so I need -5 there. So I get that from the trace. So I managed to get the eigenvalues and the eigenvectors, in fact, with very little effort. Otherwise, you have to go grind through the characteristic polynomial, which gives you a cubic, and you've got to factor the cubic and solve it, and there's a lot of work there. So just to finish off this bit, I'm going to take the eigenspace for -5. So I add 5 to the main diagonal. When we add 5 to the main diagonal, I get this matrix, and I want its kernel. Now, it's not immediately obvious what the kernel of this is going to be, so I just need a 0 somewhere to give me a helping hand. And so I'm going to add these two rows together, and that, because I can see a 2 and a -2. So I add these two rows, I get 0.66. Once I've got 1, 0, I can just write down the eigenvector now. So to make this thing dot product to 0 with the bottom row, I'll need one of them and minus one of them. So I'll take a 1 and a -1. And then I just check it on one of the other rows, say this one. So at the moment I've got 5, -1 is 4, so I need -4. And I've got a 2 there, so I'll take -2 lots of that, and that'll make this dot product with the second row to give me 0. And of course we should always check with the top row that that'll make sense. So we quickly check. You get -4 plus 2 is -2, and then plus another 2 is 0. Now I don't like too many minuses, so I've just said the span of this vector is the same as the span of that one. Doesn't matter, you can leave it like that. It's all in the same span, so I just avoid too many minus signs. Now we want to write down now our orthogonalizing P matrix, so we put down the eigenvectors. So I put 0, 1, 1, but I have to normalize it, so I've got to divide by the length, and then I had the vector from up here 1, 1, -1, and I've got to normalize that. It's got length 3. And then I've got this vector 2, -1, 1, which has got 4, 5, 6, so length √6, and you divide by √6. So this P now is orthogonal. So P is an orthogonal matrix. That means its inverse is equal to its transpose. So P inverse or P transpose AP gives me this diagonal matrix where we get the eigenvalues in the same order as the eigenvectors that I put in here. As we did with the two-dimensional conics, we're going to make the standard change a variable. I'm going to put little x, y, z to be P times capital X, Y, Z. And then when I substitute this back into the original equation over here, then I end up with this nice conic x squared, and that should be a -5 there. We end up with x squared plus y squared. -5z squared is 1. So the coefficients, of course, are the eigenvalues. And we recognise that, I hope, as an hyperboloid of one sheet. And so the easiest, and I've drawn a little picture of that, the easiest way of visualising it is to say, well, this is the same as x squared plus y squared. X squared plus y squared is 1 plus 5z squared. And then if z equals 0, we're going to get a circle of radius 1 down in the xy plane, and as z gets bigger, every cross-section is going to be a circle, but the radii are getting bigger of these circles, so I get these concentric circles coming up. That's all the cross-sections. And finally, if I put x to be 0, I get y squared minus 5z squared is 1, which is a hyperbola. So I can draw the hyperbola here in the YZ plane, and then behold the solid the surface visualizes. There it is. It's a surface which is a hyperboloid of one sheet. So that's a simple example of this. We'll have a look at a second example. So this time we're going to identify this surface. We're going to find its principal axes, and we're going to find the points furthest and closest and furthest, if any, from the origin. So this is another example of one of these conics in 3 dimensions. And here is the word solution for this one. So here's our conic. You might like to try this, might like to stop the recording and try this one yourself without looking at the solution, and then compare it with what you find. You can then compare it with the solution I'm going to do here. So again, we put this into matrix form. We've got 5, 4, 5 on the main diagonal. I've got an 8 here, so I share that equally. There's no xz term in here, so that's 0, 0. And there's a minus 4yz, so it's minus 2, 2. Now, if you quickly calculate the determinant of this thing, you find the determinant is in fact 0. So lambda is 0 is an eigenvalue. And also lambda equals 5. If I subtract 5 off the main diagonal, if you look at the top row and the bottom row, I'm going to get 0, 4, 0, 0, minus 2, 0, which are obvious multiples of each other. So lambda equals 0 because the determinant's 0. And then lambda equals 5 is fairly obvious. And then from the trace, we get lambda equals 9 for the other eigenvalue, because the trace of this is 14. Now the eigenspace for 0, well again, if you just stare at this minute, look at the bottom row here. If I take 5 of those and 2 of those, then this will dot product with this to give me 0. And then I look at the next row up, I've got 20 minus 4 is 16, so I need minus 4 times plus 4 to give me the minus 16. And then you can check it on the top row. We get minus 20 plus 20, so it dot products to 0. If you subtract 5, I haven't done the arithmetic here, but if you subtract 5 off the main diagonal, then you'll need to kill the middle entry. And then having done that, you look at the middle row, which would then be 4 minus 1 minus 2. And if you take one of those and 2 of those, you'll get 4 minus 4 is 0. So it's fairly easy to write down the eigenspace for lambda equals 5. Lambda equals 9, well I had to do some work here, so I subtracted 9 off the main diagonal. You look at the top row and you say, look, I'll have one of those and one of those. But you soon discover you get fractions if you do that for the third one. So I'll take 2 of those and 2 of those, and that'll dot product with this to give me 0. And then the middle row gives me 8. Minus 10 is minus 2, and I need a plus 2, so I need minus 1 times minus 2, and then you can check it on the bottom row. But it in fact dot products, each of these dot product with this to give me 0. Now our orthogonalizing matrix then P, now what did I do? I put 9 firstly. I took the biggest eigen, you don't have to, but I just chose to put the biggest eigenvalue first, so the eigenvector corresponding to the biggest eigenvalue first, so that was 2, 2 minus 1. And then 5 is 1, 0, 2, and then minus 4, 5, 2. Then I have to normalize these, so I divide them by 3, this by root 5, this by root 45, which is 3 root 5. And again, we make our standard change of variable, and after doing that, we see using the eigenvalues, we see we've got 9x squared plus 5y squared, and then we'll get 0z squared is 45. Now there's no z in this equation, so that means the z-axis will be an axis of this, and it's going to be a cylinder. Every cross-section is going to be an ellipse, so it's what we call an elliptical cylinder. So here's the picture of this thing. So every cross section is an ellipse. Z can do whatever it likes, and we get what's called an elliptic cylinder. Now there's no points furthest from the origin, because you can go as far as you like up here and you can go as far away as you like from the origin. The points nearest to the origin are going to be these two here, where it cuts the x-axis, and along the capital X-axis this is going a distance of √5. So the points closest to the origin in the capital XYZ plane are capital XYZ is plus or minus √5, 0, 0. And we'd like to know what that is back in terms of the little xyz. So we simply multiplied this by the matrix P, and you'll get a √5 from there. If you look back to P, you'll get a divide by 3 over here, and you're just picking off the first column, so you'll get 2, 2, minus 1. So they are the points that are closest to the origin. By the way, just one final observation here on this. I did not attempt to draw the little x, y, z axes. You end up with a very complicated diagram if you attempt. I'm not sure I would dare do it. If you try and actually plot the eigenvectors and have the old axes here, it makes the diagram very complicated. So in the three-dimensional case, we generally only show the new axes. Now, we can now classify some of these quadric surfaces. So we talk about the classification. We've seen that we can write one of these quadric surfaces in this shape. We can put it into what's called canonical form, or standard form, which simply has an x and a y and a z. And of course the lambda 1, lambda 2, lambda 3 are the eigenvalues of the symmetric matrix. Well, what sort of surfaces do we get? Well, I'm going to assume G is positive, otherwise you've got a sum of, well, you could have a sum of squares to be 0 or negative or something. So I'm going to assume G is non-negative. Then the shape depends on the signs of the eigenvalues and whether G is bigger than 0 or equal to 0. So if all the eigenvalues are positive, then obviously we're going to get an ellipsoid. If they're all equal, of course, we'll get a sphere. If we've seen that if 2 are positive, 1 is negative, you get a hyperboloid of 1 sheet. If you get 1 positive, 2 negative, you get a hyperboloid of 2 sheets. Now, if G was 0 and they're all positive or all negative, you only get the origin. If G is 0 and we get 2 positive, 1 negative, or 2 negative, 1 positive, then we end up with a cone. There are other possibilities occur when one or more of the eigenvalues is 0, as we've just seen in the previous example. The most important are when, for example, if you've got 2 of these positive and the third one 0, as we just saw, you get an elliptic or possibly circular cylinder. If 1 is positive, 1 is negative, and you get 0, and G is positive in these cases, you get a hyperbolic cylinder. So these are the different situations that can occur in the case of three-dimensional conics.